In this example, we've got a two-span continuous beam with a couple of loads, and then we add some support settlements. So in reality, this situation is one that's pretty complex, and we're going to go through an execution of the slope-deflection method to figure out what the member end moments are, from which then after that everything's just equilibrium. But to get there is fairly complex, so let's in a lot of work. So let's try to understand how this all might work, so that we have a way to understand whether our detailed work at the end is going to be satisfactory. All right, so let's get into more details here. The two outer spans have the same length, they have the same flexural rigidity, so with the same length that also means they have the same flexural stiffness. We got two fixed ends on the outer edge, and we've got the roller supports in the intermediate. That middle span has twice the flexural rigidity, but because it has a longer span, the EI over L of the member will be a little bit less than it would have otherwise been. But it's still, overall, you probably expect that the middle span is stiffer than the two outer spans. Right? We don't have the same magnitude distributed load, so that's going to influence what happens, and then we get this support movement. Now we're in the SI system, so sometimes that we're not as familiar with the magnitudes of things. We have a support movement that is about 10 millimeters or 1 centimeter. Right, so that's about a 1/4 inch-ish, yeah, a little more than that, maybe 4/10 of an inch or so, 2.54 centimeters per inch. So 1 over 2.54 is going to be roughly that will be roughly about 4/10 of an inch. So only maybe 1/2 inch of differential settlement over this span of 5 meters, which is on the order of about 17 or so feet. That doesn't seem like a whole lot, but I don't know. When you have these kinds of stiff systems, a little bit of support movement can have a fairly large impact. Wow, I mean, it is a bit complex here about what's going to happen. So let's do this. Let's break apart these effects in terms of our guesses into 3 pieces. One that's associated with just the load on the left, one that's associated with the load on the right, and then one just only associated with the distributed load. Now we're only going to do this breaking apart or superposition for trying to get our informed speculation and anticipation of what's going to happen. After that, when we execute the slope deflection method, we'll do all of this all at once. So what I do when I'm faced with a situation where I'm not really certain what's going to happen, not only do I break it down, but I draw what I anticipate is going to be the deflected shape or something like that. And I'll start with the things that I know for certain are going to happen, and that is at the fixed end I have no rotation, and in this left-hand span certainly our system is going to curve downwards initially, and then it's going to want to try to curve back up. We get some smiley face. The thing of it is that we don't have a fixed end over here at this roller. Instead, it's going to we got a little bit of things happening, flexibility that is, in the mid-span. So I guess we're going to swing up a little bit, and then that middle span is going to want to kind of pop up a little bit, and it's going to want to pop up such that we're going to cause some rotations at the far end that are, well, I don't know how far that's going to go. That may actually continue on a little bit here. Yeah, I don't like that. I don't like that because, gee, now we've popped down, which means that this is going to have to go down here, and it means that we've got to pop back up over in here. You know, that's kind of, well, I'm not sure what's really going on here, but one thing I do know for sure, this left span goes down, the middle has to pop up, that has to pop back down. There'll be a nice little S-curve that shows up in this span right here, and then it'll kick back over and be hogging curvature in the middle. That's about the only thing maybe I understand for sure. Now we go to the next one, and same thing, we're going to come down a little bit. Oh, hey, you know, this is going to end up being a mirror image of what we had over on the other one. Not the same magnitude, but certainly a mirror type image, because we've got the load pushing down that right hand span, causing the middle span to want to pop up and causing the far span to want to go down, but it's going to have that support at that outer edge that's going to want to try to kick things back over. And if you noticed how I just drew that this time, it was a lot smoother. I was probably pushing the inflection point in my first one in the wrong part of the span. That's why it was so hard to draw that one. And this time I pushed that inflection point further to the fixed end, and it actually made it quite a bit easier to draw that. And there's an important point to make out of that. Then is if it's really hard to draw it, as in it's hard to get these curves in here, it's hard for the beam to do it too. So if you find a way to draw it that's easier, smoother in terms of aligning all these little curves in the French curve to reflect what that might be going on, that's how the structure is probably responding too. Right? So when I say hard, I don't mean it's hard for you to move your hand and make it happen. I mean it's, well, I do actually mean a little bit of that. It's all about how you use the French curve to make this happen, and that's something reflective of what's going on in the structure. Alright, so what this has told me so far is that these two loads are, well, to use the street language, simpatico, meaning they cause the same kinds of effects. And so they'll magnify the effects together, that when I add these two together, the middle's going to pop up even more, and the ends are going to move down a little bit more. But when we get to the support movement, support B moves downwards by 0.01 meters, or that about 10 or 1 centimeter. You know, that's kind of a big deal there, and that's going to make things go differently. Now, if it was a fixed condition in that move down, I'd have the S curve, but you know, we got a little bit of again of flexibility here in that middle span compared to that fixed end approach. That's going to relieve some of this, but notice what we get. Frowny face at the left. Oh, that will magnify the same frowny face we're getting, or negative moment, in the other two situations, but we're going to relieve some of the frowny moment or negative moment that we have from the loads with that support movement. And what ends up happening with the rotation here? Not exactly certain. If this was isolated, this would be frowny face all the way. If we had fix, we have frowny face and then smiley face. So this has a little bit of flexural stiffness, so we'll be somewhere in between. Okay, so I think what that means is that the inflection point is maybe out in here, and we'll have some smiley face, but we'll have a net clockwise rotation caused by the support movement, just in isolation. So I'm going to lay out the French curve here, and in a way that matches, of course, zero slope at the left, big sharp curvature. And you note that I'm kind of moving the French curve. I want this to dive down below, because that's what would cause me to have to meet the boundary condition I've got here and swing it back up, or positive moment, positive smiley face kind of curvature there. And when we do that, now I've got the beginning of what's going to happen here. Now what happens in the right part? Well, I probably end up with a little reversal here that's going to kick things around. That's going to, let's see, this is going to pull this down. That means it's going to push this up. This will be swinging up, coming back, and I don't know really, I guess I'm not really certain again what happens over there. So I'm just going to make some guesses, try to make it not too exaggerated. Get it kind of begun to swing over, and then let's see, that's going to be maybe something like this. start to get it to come back down, and then we'll smooth it out at the end. If that had only been a roller support at the far end, this would have just popped all the way over here in a nice hoggy curvature. But that fixed end means I got to swing it back around again. And what that tells me is in every single span, in almost every region, the support movement is going opposite of what all the rest of this is doing, except for this far left edge. Wow, you know, this takes a long time to kind of figure out what maybe is going on here. And so, well, I don't know, other than things are gonna get kind of less as a result of the support movement. Now, if we were just talking fixed, and I put the load on here, I'd get fixed in moments. That would be WL squared over 12 and minus WL squared over 12. Right? And as a guess, then we could start with that. We've got 80 times the span 5 squared divided by 12, and that's 166 point change, so about 167. This other one's going to relieve it, and I don't have any idea how much. We've got a little magnification that probably is happening from the load way on the right, but it'll get diminished as we go along. It's going to be bigger to start with a fixed end moment, and then get relieved as this joint rotates. That'll get carried over by a half, so this turns out to be, let's see, 10 to 8. That's increasing by 25%, so we're up to same span, so times 10 divided by 8. Oh, that's about 208, comes over at about half of that. So now we're up to about 271 here, but I don't have any idea how much gets relieved by this effect over here. On this one, maybe I'm going to guess, again, it's just from these alone, I'd say we're going to be on the order of 250, 300, something like that maybe, but I don't know what's going to happen, all because of the magnitude of the effect of the support movement. So this is kind of a tough one to try to guess. Right now I think this is going to get closer to 0. This one's going to get bigger than the minus 167, so I'm going to guess here about the order of minus 200. This on the order of, well, 0 seems way too low, so I'm going to just guess about 80, and this I'm going to guess on the order of 250. This I'm going to guess on the order of I don't know, 208, throw a little effect over there, maybe 225, and plus or minus, depends what sign convention you want to use, slope deflection or the moment distribution. But this, by the way, I was just using as the aggregate of my answers. We'll see how that plays out in the next phase.